Hi, today we'll discuss about some uh, PIC architecture, so which is most popular in all the 8-bit microcontrollers. Okay, why? Because it is having very high speed and among the all 8-bit microcontrollers. When coming to 8081, AVR, all these microcontrollers work with very less speed. Okay, so better performance is having PIC architectures. Okay, that's why we are going for PIC architecture. So it is having high performance in all among 8 gen 8 that is 8-bit microcontrollers. It is working with high speed. So now we will discuss what is PIC and why it is popular. Okay, so when coming to PIC, it was initially introduced by some general instruments with 16-bit CPU. Okay, with some basic input outputs. Okay, so that the name was CP1600, but the CP1600 is having some light poor performance. Okay, so due to that reason they have developed an 8-bit microcontroller which was developed in 1975. So the reason for to develop this one is to improve the performance of the overall system by uploading the input output task from the CPU. That means externally they have given some peripherals and they have developed some 8-bit microcontroller. Okay, so PIC basically uses some macro codes, that is predefined codes are there, which are some, if you write some assembly codes, the upcodes will detect the macro code. Upcodes like that, like upload codes, upcodes for assembly instruction. The microcodes will be present in ROM of the microcontroller. Okay, so whenever you want the processor want to execute these assembly instruction, it will compare the upcode with the macro code, then only it will execute. Okay, if the instruction is not found, then it will give some errors. Okay, it will stop the execution. So it shares some common features with the RISC design, as PIC is a RISC property. Now we will see in the next slide what is RISC and how it is how the instructions will be. And the main acronym for PIC was Programmable Interface Controller, given by General Instruments. Okay, the first PIC series developed is PIC 1640 and PIC 1650. Okay, so recently they replaced the acronym as Programmable Intelligent Computer. So you can say PIC as Programmable Interface Controller, or you can say Programmable Intelligent Computer. Now, what is, as I told you, PIC is a RISC property. So what is the difference between what is RISC and what is CISC? Okay, RISC stands for Reduced Instruction Set Computer. Similarly, CISC stands for Complex Instruction Set Computer. Okay, when coming to RISC, it is having some properties. So you can see here the basic architecture which are using RISC are Spark, Alpha, Atmel, AVR, different micros like PIC, ARM. All these are with RISC properties. So the main three properties which I tell you, the RISC are having mainly three properties. One is all the RISC versions which are having all the instructions are executes in single cycle. That is one property. And second property is all the instructions are having fixed length. That means if you say that is 8-bit instruction, the processor will execute all the instructions with 8 bit. Okay, and there are very less number of instructions, that means usually less than 50. Okay, and RISC supports pipelining stages. That means execution of instructions in the parallel, that is pipelining stage. Next, when coming to CISC, opposite to the RISC, so as it is having all the instructions are executed in single cycle, it maybe takes several cycles for execution of the single instruction. Okay, and one more thing is RISC is having few instructions. When coming to CISC, is having very large number of instructions which we can't remember. Okay, that is very greater, that is greater than 100. Okay, which are used in 8051 8066 architecture. Okay, and all the instructions are of different length. Okay, that is given several addressing modes. That means all the instructions are of different length. Each instruction may execute in different cycles. So this is the main difference between RISC and CISC properties, and our PIC architecture support RISC property. Okay, and why PIC is more popular, that we'll see now. As I told you, it is a high speed controller among all 8-bit microcontrollers. And what are the remaining reasons for because PIC is popular? Okay, first point is that it is very low cost and wide availability with high clock speed. Okay, so it is in the market, PIC is available with very low cost. Okay, so when compared to 8051, it is 8051 is not having any inbuilt peripherals. Okay, and it is very low speed. So when compared to PIC, 8051, it is having all the input peripherals, no need to interface any peripherals external like ADC, UART, all are having internally, and it is coming with very less cost. And suppose if you want to write an application for, if you want to develop an application for the PIC architecture, we need different development software development tools. Okay, so those software developments are available very low cost. Okay, and it is having a, as I told you that the PIC supports a RISC property. It has having only 37 assembly that is instructions. Okay, if you want to write some 100 instructions of code, all these 37 instructions may be repeated several times. Okay, only thing is it is having only 37 instructions. And if you want to program, suppose as we write any application for the PIC development, if you want to write any program, okay, that is if you want to dump the output hex file into the PIC programming flash programmer, we can use serial programmer for programming and reprogram. That means you can write the data, or you can erase the data from the flash, okay, by using the serial communication. Okay, that is, it supports in system programming. Okay, when coming to 8051, so 8051, if you want to program any 8051 microcontroller, we need to remove the IC from the application board, we need to place in the 8051 programmer separately. So after programming, again we have to place in the application board, then we have to execute that one. So not like that here, it is inbuilt, it will be, the PIC IC will be present in the application board only, we will program through serial programmer. Okay, that is serial communication. So it is very small, the PIC is very small and easy to implement for non-complex problems, and usually accompanies to the microprocessor as an interface. That means nowadays there are non-complex problems like basically some DSP algorithms, all these things, new end versions of PIC which is releasing with the DSP processors with a very low cost when compared to the DSP processors. Okay, so we can easily execute the non-complex problems with the PIC microcontroller when coming to all other 8-bit microcontrollers. So as I told you, PIC supports RISC architecture. Among that one, another property is Harvard architectures. So we know there are two versions, one is Harvard and another is Von Neumann. So Harvard stands for whatever the memories, that is program memory and data memory, access with the microprocessor with separate buses. There are two separate memories and two separate buses for the program and data memory, which are accessible by the microprocessor with two different buses. That is, it is having two separate address and data bus, or separate program and data bus for the memories. Okay, when coming to Von Neumann architecture, there is common bus for both program and data memory. Okay, so which is faster? We can say Harvard architecture is faster. So why? Because we can access both program and data simultaneously. When coming to Von Neumann architecture, there is only one bus, either we can access the program or data. Okay, that's why Harvard architecture is very speed when compared to all other microprocessors. So every processor executes the instruction depending upon the clock cycle. Whatever the input clock cycle we are having, depending upon that clock cycle, it executes the instructions. When coming to PIC architecture, it takes the different PIC versions will take different clock cycles. When coming to PIC 18 family, it takes 10 MHz clock, and it is having internally some PLL. It will be multiplied with 4, then it will be converted into 40 MHz. These 40 MHz is again converted into 4 cycles. Like you can see here, that is Q1, Q2, Q3, Q4. This is complete. Whatever that 40 MHz that we are in, each cycle is converted into again 4. But you can read here, the clock from the oscillator enters into a microcontroller via oscillator 1 pin. That is oscillator 1, oscillator 2 pins. We are connecting some external 10 MHz oscillator. The microcontroller divides the clock into 4 even clocks, that is Q1, Q2, Q3, Q4, which do not overlap. These 4 clocks make up one instruction cycle. Instruction will execute in these 4 clock cycles. Okay, also called this is mention cycle, during which one instruction is executed. When execution of instruction starts by calling an instruction, that is next string. Okay, so as well it is a RISC property. It is having fetch, decode and execute 3-stage pipeline. Okay, so we can see here the fetch and decode executions, how they are executing. Decoding and execution of instructions are done between the Q1 and Q4 cycle. On the following diagram, that is here we can see here, and the program counter holds information about the address of the next instructions. Okay, now you can see whatever the data sheet we are providing, like PIC PDF, the data sheet we will provide. So in this one we can preview how external clock input will work, and what are the how we are giving, and how it PIC PLL will multiply or divide the oscillator, that is whatever frequency whatever giving oscillator 1 oscillators we are giving physical oscillator, this is F in and this is F out. If you don't want to PLL, then directly the PLL will be directly given to the system clock. If you want to enable PLL, it will do some operations. If you want to multiply or divide the PLL, so here you can see if you use PLL, phased local loop circuit provided program may be optionally. So for an input clock frequency of 10 MHz, the internal clock frequency will be multiplied to 40 MHz. This is useful for customers who are concerned with the EMS. So that means if you want to enable PLL, it will work with 40 MHz, and this 40 MHz again will be converted into 4 clock cycles. Okay, in these 4 clock cycles, the instruction may be executed. Okay, that means all fetch, decode, execute. Suppose one instruction is fetching, so now we'll see in the next class how they are executing. Okay, you can see here, this is first cycle, this is second cycle. In the first cycle, one instruction is executed, that is fetched from the memory. Okay, whenever it is fetching from memory, it will execute in the single instruction, and in the next instruction it will go to the execution stage. In the, whenever it is executed in the same instruction, another instruction may be fetched from the memory. That is, two instructions are executing, but is this one clock cycle, this one, the instruction may complete in 2 clock cycle, but it will be completed among these things only one instruction is executed. That means complete. That is, if one instruction is fetching, another instruction is executing, that means complete one instruction is executing here. That means the process of complete instruction is completing. Okay, so for that reason we are telling that risk property instructions will execute in single clock cycles. Okay, so fetch takes among Q1, Q2, Q3, Q4, complete these things will be done, that is fetching and executing. Okay, so suppose there are some instructions which may execute in 2 clock cycles. There are like whenever program counter occurs, or branching instructions occur, so these means, okay, all instructions are single cycle except for any program branches. So suppose if you want to jump from one program to another program, one function to another program, if there may be branching from one address to other address, in that cases it takes 2 clock cycles to execute that one. Why? Because to fetch the address from memory and we have to place in the program counter, that will takes 2 instructions. Okay, so now we will deal about discuss about microchips PIC18 family. There are I told you some DSP PIC is also there, and PIC microcontroller units also there, so which are coming in the in versions. So initially PIC10, 12, 16. Now we are dealing with PIC18 family, which is having these properties, which executes the instructions in 10 to 12 MIPS, and it is having up to 120 KB of programming flash memory, and it is having 18 to 100 pins. That is the pin package will be different. So when coming to these things, all which are present in below, all are 8-bit microcontrollers, and when coming to these things, all are 16-bit microcontrollers. Okay, so now we'll see first low-end microcontroller, PIC microcontrollers. First thing is PIC 8-pin package, that is dual in-line package or small outline package. So here you can see the basic version of the PIC microcontroller. It is having only 8 pins, and it is having 5 GPIO pins. So now you can see the properties and now the instructions will be. It is having 33 instructions, and the clock frequency is 1 microsecond instruction time, that is 4 MHz clock it is saving internally, and it is having 512 12-bit program memory and 25 8-bit data memory, and 2-level hard stack, and it is having 5 GPIO pins and 1 input pin. You can see here GPIO 0, GPIO 1. Okay, and this is GPIO 2, and 1 clock pin, 1 input pin here. And what are the features? Internal pull-out, wake up on pin change. Okay, that is if you giving any pin, that is there is one pin, one input pin, right? If you give some digital signal, one unlock signal or digital signal to this input. Suppose if you want to, if there is suppose one digital signal is present, if it is continuously positive, okay, high level, when suddenly it changes low level, it detects it. Okay, that is a pin change, wake up on pin change. Okay, and peripherals, it is having timers, watchdog timers, and this is the cost of the $1. Okay, I mean if you would take $100, this is maybe a cost. Okay, if you take one IC, this is the cost, and if you take 100 IC, this is the cost. If you take more than one, complete with these things. And the next version is PIC16F family, which is having some 28-pin package. So it is having some inbuilt peripherals when coming to before one. Okay, it is having only GPIO pins. It is having some external, that is inbuilt additional peripherals. Okay, like ADCs, USOT, I2C, SPI, 16-bit and 8-bit timers. Okay, and it is having some properties called Brownlow detector. Brownlow detector means, suppose if a microcontroller is working with 5 volts, whenever the 5 volts decreases to some another 4.5 or 4 less voltage, then it will detect it automatically. The processor will reset the memory and will shut down. Okay, that it won't shut down, it will directly reset the program whatever is present in that one, and again it starts from executing. If that is 5 volts, then it will start executing, otherwise it will stop the execution. And it is having in-circuit debugger property. In-circuit debugger means, suppose some instructions are executing in the programming, how the instructions are executing in the processor, that we can see in the by connecting some in-circuit debugger protocol. We can see that one, like JTAG protocols. Okay, and it is having 28-pin package, and these are the instructions time, how these are executing. And this many flash memory in the EEPROM data memory, that is non-volatile memory. You can store separate data in the EEPROM, and 22 GPIO pins it is having, and these are the peripherals. Now we see next family, PIC17C family, that is 17 version family. It is 84-pin package, and it's coming with 58 instructions, and this is the clock frequency, and each instruction executes in these nanoseconds, 121 nanoseconds. This is the program memory, data memory, and these are the out of 84 pins, 66 GPIO pins are there. And these are when coming to 16 family and 17 family is having these many additional peripherals, like Brownlow detector, microprocessor mode, that is operating mode, and 8 into 8 multiplier. So when you multiply 8-bit into 8-bit values, it will give 16-bit results. So there are no 16-bit registers, right? So if any processor which supports 8 into 8 multiply, there are some registers, high and low register. That means two 8-bit register which stores the result of 8 into 8 multiply values. Okay, and it executes two 8-bit instructions, two 8 into 8 multiplication in a single instructions. So if you want any further advantage, if you want any details, just to go to the PIC datasheet which we have given. In that one, 8 into 8 hardware multiplier peripheral chapter will be there. Just go and go through that one. Okay, if you want, I will show you that one. This is the datasheet which I have given. So you can see here 8 into 8 hardware multiplier. You can see and you can read this one, how many instructions it is taking, how many clock cycle it is taking, if it is 40 megahertz, 10 megahertz, 4 megahertz. Okay, so go through this one later. Okay, and what is the different PIC families and PIC packages? When coming to 8 pin, 18 pin, 28, 40, 44 to 64. Now is in the previous slide we have seen some 84 pins. Okay, so these are 17 families, 12 families, different. Some version to version there are many changes. There is speed is also increases, and package is also changes. Okay, that means first version 8 pin, after that 18 pin, after 28, 40, 48 number pins also increasing, the packaging also increasing, and inbuilt peripherals also increasing, and speed also increasing. Okay, so each family, how it is taking, how many instructions it is taking. When coming to 12-bit code, it is taking 33 instructions. These are the families. When coming to next families, it is taking 35 instructions. All these are RISC properties, so there are fixed number of instructions. Okay, so when coming to 17 family, it is taking 58 instructions. When coming to 18 family, it is 77 instructions. Now we are dealing with 18F microcontroller, right? It is having 37 instructions. Okay, so what is the speed? I told you, right, it takes the clock oscillator externally and divides multiplies into the 4 times, that is 40 megahertz. It will give 10 megahertz as the input. Okay, so if you don't use any external clock, so simple PICs have inbuilt 4 megahertz RC clock, so not very accurate, but requires no external components if you use this one. Okay, so it can, for external things you can use crystals, clock oscillators, or even RC circuit also to generate a clock, and you can use the externally. So instruction speed will be 1 by 4 into clock speed, how much clock speed, and timer clock is equal to 4 into timer clock cycles. That means each cycle is instruction cycle. So this is different clock for different families. And program memory. So each and every architecture, each and every family is having different program memory. Okay, so when coming to 12-bit, that is 5, it is having 12-bit instruction, it is having 512 bytes of memory. And coming to 14-bit instruction, it is 1K, 14-bit 18K, 8K, 16K. Now in version 32K program memory is also there with the technologies EEPROM, flash, ROM. Okay, so data memory, according to the program memory, there is additional RAM which we can store current executing RAM data, that is random access memory, which is volatile memory. After the execution, after if you power up, all the data that will be stored in the RAM, that will be gone, not like non-volatile memory. So each and every peak microcontroller, every microcontroller is having some data memory, that is RAM memory. Okay, these are the sizes of data memories for different versions. So when coming to PIC 18, what are the common peripherals, common inbuilt peripherals that are present in the microcontroller? Now we can see digital input output ports. Now each port can work it as input or output, and analog comparator in that one, analog to digital ADC, timers, capture, compare, PWMs, capturing the signals, okay, comparing the signals, and PWM generating the pulse width modulators, and UARTs, asynchronous, that is universal synchronous, asynchronous receiver and transmitter, that is addressable, that means there is only one UART which is present, we can directly access. Okay, and MSSPs, master synchronous serial ports, which in this master synchronous will all the ports will work with based on the clock, like I2C and SPI. So which are basically working, the I2C is a 2-bus wire and SPI is a 3-bus wire. Okay, so what is I2C, what is SPI, we will see in the next classes. Next, parallel slave port, it supports upon parallel slave port protocol also, parallel communication. Okay, next, how the simple block diagram of the microcontroller unit architecture. So, okay, so this is program memory and this is data memory, how it is CPU is executing each instruction, how it is taken from the table, how it is, this is program bus and this is data bus. This is a Harvard architecture, it is having two separate, it fetches the program in 16-bit but executes in two different, if it fetches in 16-bit also, it takes it separated into two instructions again in that one, and again it been 8-bit instructions. Okay, so it is having data RAM, peripherals, and input ports. This is the main block diagram of that one. So when coming to PIC 18 family, in PIC 18 family there are different series, PIC 18J, PIC 18K, PIC 18F, like that. Okay, each different series having each different properties. Like when coming to basic PIC 18, it is having 40 megahertz input clock, that is working clock, and 10 MIPS, 10 million instructions per second, and it is working with 5 volts and flash memory of 100K and EEPROM features. 18J series, these are the properties, and it is working with 3 volts. Okay, and it is having the most effective 32 KB flash, greater than 30 KB flash. And coming to PIC 18K, it is working with 3 volts and 16 MIPS, that is highest version in the PIC 18K. The PIC 18, no, not in PIC 18K. There are different versions which are having greater than 16 MIPS also in PIC microcontroller. Okay, and most cost effective, that is less than 30, that is EEPROM, the size will be very less, flash memory, but it is executing very speed. So when coming to PIC 18F family, what is the architecture of the microcontroller, how it will be? Okay, so you can see here this is complete processor unit, and this is the bus unit, and this is the program memory and data memory. How the programming data memory is accessing from the CPU, that is 21-bit address and 16-bit instruction or data bus. Okay, if in the program only, if you write any data or anything, that will be fetched from 16-bit data, and the instruction will be executed from the 21-bit address bus. Okay, in the data memory, the data will be fetched from 12-bit address bus and 8-bit data bus. Okay, and that is data will be fetched from the 8-bit data bus, where the data actually presented, that will be fetched by 12-bit address bus. Okay, and it is having VSS, ground, external clock, and reset, interrupts, all these things. And you can see in the processor basic, any RISC property supports some arithmetic logic, any processor supports arithmetic logical unit and some working registers, and the status of the processor, and instruction decoder, and this registers called blank selection register and file selection register, program counter. So we know all the program counter, that is which stores the address of next instruction which is to be executed. Okay, this is the basic architecture of PIC 18 family. If you have any doubt, just to go through the PIC datasheet which we have given. Okay, so and what is the program, how much program memory and how much data memory it is having. So it is having 21-bit address bus, so among that one total 32 KB of program, that is 32 kilobytes of program memory we can access. When coming to data memory, we can access 4 KB of data memory we can access. Okay, so in this data memory, all the data registers, file registers will be present. Okay, so this is 32 KB of 4 memory. The range is from 0 to 3Fs. And when coming to data memory, it is having 4 KB of data memory, that is 0002 FFF. Okay, and data EEPROM, separate to the data memory, it is volatile memory. When coming to data EEPROM, it is non-volatile memory. Once if you store in this EEPROM, there is going to be erasing option. That means we have to erase that one. Until and then it won't be deleted. Okay, this is non-volatile memory which is present in the each and every PIC microcontroller, that is which supports the EEPROM, data EEPROM. So when coming to PIC 1845, it is having 256 bytes of EEPROM. So address bus, so as we see now, the address bus, how much 21-bit address bus, we can access 2 MB of memory. So among that one we are accessing 32 KB of programming memory. So when coming to data memory, 4 KB of data memory with a 12-bit address bus. Okay, so these are the address buses. That means how suppose some instruction, some data is there, where the address of the data, where the data is stored, that address we are fetching from the address. Okay, that address we are taking from address bus, and the data we are taking from data bus. Okay, that is we said no, this is a hardware architecture, there is separate address and data bus, right? So there are addresses, address will be fetched separately and data will be fetched separately. Okay. And how the arithmetic and logical unit in the processor will be, the architecture will be. Okay, it is having some instruction decoder, 16-bit instruction decoder, and it is having some status. What is the status of the processor? If the processor executes any instruction, if performs any arithmetic operations, how it will execute instructions. That means how we can say, suppose if you perform any addition operation, if there is any carry occurs, if there any negative result is there, if there any zero result is there, all these statuses will be updated in the status register. And there are some working registers which are present, and 8-bit, like 8-bit accumulator registers which are present in like 8051, AX, BX, all those registers that are like there is same working registers are there. The processor work with these registers like our general purpose registers, R0, R1, R2, R. These registers are working registers here. Also this is about status registers, as this is having 5-bit status, that is negative, overflow, 0, digit carry, and carry borrow. These are the basic 5 status bits in the, this is the description of these things. Okay, and what are the registers? Program counter. So whenever you fetch any address, the address bus will be 21 bits, right? 21 bus width, right? So that's why we have 21 bit register function as a pointer to program memory during the program execution. And table pointer which specifies the way to the memory will be accessing. Okay, pointer to copy the bytes between program memory and data registers. And next one is the stack pointer, which stores the stack address of the, that means stack means where your current temporary data will be storing in the stack memory. The top of the stack will be accessed by stack pointer. And 31 registers used for temporary storage of memory addresses during execution of the program, that is in the stack pointer. Next, bank selection registers and file selection registers. What is the bank selection and file selection registers? Okay, so whatever all the data registers and that is basic working registers, all these are present in arranged as in some banks. You can see in the next slide. So this is complete banks. Total it is having that is 16 banks are there, and each bank is having 256 bytes of memory. Okay, so complete thing is data memory. How much data memory we are having? Totally 4 KB of data memory, right? So that 4 KB complete data memory is arranged as 16 banks with each 256 bytes of one bank. Okay, in each one bank there are general purpose registers and special function registers are there. Okay, so how these things, bank selection registers are arranged. Okay, so where the register is present in each bank, the bank address will be indicated by 4-bit registers. Okay, so the 4-bit registers indicates where actually the bank is, that is bank selection registers. This is a 4-bit bank address from 0 to F. So which bank the register is present? Okay, so 0 to F, this 4 bits indicates the where the, that is a bank address. Okay, and file selection registers, there are 3 file selection registers which are composed of 2 8-bit registers, as the instruction will execute in 16-bit instructions, right, internally. So we are having 2 8-bit registers, high and low. Okay, used as pointers for data registers. These are used as pointers for data registers. For fetching the data will be loaded into file selection register, then you can execute this one. So holds 12-bit addresses of data register. The address of, as we know, the for the data memory there are 2 buses, right? Again, data memory also, one is address bus and another is data bus. So data bus is of 12 bit, and address bus is, that is address bus is of 12 bit, and data bus is of, that is 12 bit address bus and 8 bit data bus, right? So here also it holds the 12 bit address for the data register. The register is 8 bit register, it stores the data, but where the register is stored, the 12 bit is stored in this file selection registers. So this thing, this is the bank selection, how the bank will be arranged in this one, how the registers are arranged in the memory, complete data memory, 4 KB of data memory with having all these general purpose registers, special function registers. Okay, so all these things. So when coming to special general purpose registers are working registers, file selection registers, all this comes under general purpose registers. When coming to special function registers, the microcontroller is having inbuilt some peripherals, right? So all these peripherals having separate registers to access them. So these registers are input output ports like interrupts, EEPROM, serial input output, timers, UART, capture compare, or ADCs. All these are separate peripherals, right? So these are having separate registers to access them. So these are special function registers. Okay, so in that data sheet of PIC 18 data sheet, you can go through the each and every peripheral and how the registers are there, that we can see in the, when you are doing with the each and every peripheral working, then we will see how to access registers, all these things. And the special features of the PIC 18 family. So it is having sleep mode, that means it, whenever the when a processor is execution stops, it will directly enter into the sleep mode. That means the power, that is the clock, will be stopped to the processor, then the processor will be in the standby mode. That means still sleep mode is called standby mode. Okay, and watchdog timer. Watchdog timer is one such property called which continuously monitors the, that is what it continuously watches the memories. Okay, whenever any memory overflows occurs, then it will generate an interrupt, that is called software interrupt, generate automatically. Then whatever the overflow occurs will be generated using the watchdog timer. And there is a code protection in the flash memory, and it is having in-circuit serial programming, that is in-system programming, and in-circuit debugger. Within the circuit only we can see how the instruction is executing by connecting additional external protocols, in-circuit debugger protocols like JTAG protocols. Okay, and this is the IC diagram which we can see in the architecture. So this is PIC 18F452 family or 442 family. Now we are using PIC 18F452. This is the series. So in this PIC 18F452, how it look like? What is the pin diagram? So okay, it is having total 40 pins. So it is divided into total 5 ports: port A, port B, here port C, this is port D, and port E. So okay, port E is having 7 pins. Okay, that is RA0 to RA5 and RA6. You can see RA6, which is reserved for some oscillator 2. If you use the external oscillator, it will be gone. Okay, so for that one we will say 6. Port A is having 6, total 7. So RA6 is for oscillator 2. Total port A is having 7 pins. And when coming to port B, it is having 8, and port D 8, port C 8, and port E is having only 3 pins: RE0, RE1, RE2. So port A is 7, 8, 8, 8, and 3 pins. Port E is 3 pins. So we will say as port A is having 7 pins, but we will say only 6 pins. Port is having only 6 pins. So that's why 6, 8, 8, 8, 3. Why? Because one port pin of the port A is reserved for some oscillator, external oscillator. Okay, so on each side we can go for VD and VSS, and we can take the VSS and ground. Okay, and each port pin is indicated by RA0. For example, if port A 0th pin is indicated by RA0, and port B, that is 0th pin indicated by RB0. For example, if port D 0 pin is indicated by RD0, like that. Okay, and each pin is having multifunctionality. That means not only the single pin. If you take RA0, it is a digital input. Not only digital input, it can also work as analog input 0, as it is having ADCs inbuilt peripheral, right? So in that one, it is having total 8 channel ADCs, 10-bit ADCs. In this one, this is the one channel, AN0, AN1. This is second channel, this is third, fourth. Okay, you can see the 5th one, this 6th one, 7th one, and this is 8th one. Total 8 channels are there, 10-bit ADCs. Okay, so all the channels are reserved for port A and port E. Okay, if you want to use ADC, if you want to connect any ADC input, if you want to connect any sensors, you can connect all to these 8 channels. Okay, you have to configure this as ADCs, then you have to connect this thing. And the first figure you are seeing is MCLR. This is a master clear pin. Okay, the it will connected to the reset pin. Okay, any application board will contain reset switch, right? So the switch is connected to this pin. Okay, this will be by default low. Whenever you press that switch, it will give it high. Then the complete data memory, the complete microcontroller will be reset. Then it start executing from the again first. It will execute from starting stage. Okay. So here we have to give the oscillator, external oscillator, oscillator 1 and oscillator 2. Okay. And these are the different ports. And you can see here PCB is the programming the data memory. So as I told you that this system programming, you can program through and reprogram using serial communication. So in the serial communication guys are connected to these three bits: PCB, PCC and PCS. So PCB stands for programming data and programming clock, and next one is programming enable pin. Okay, by using these three pins we have to connect the pin. Okay, that means the program will be continuously stored in the flash memory from this programming data memory, and this is the clock pin for that one. So this is the enable pin. So these are the programming pins. Okay, that's why and it is having interrupt. Okay, interrupt 0, interrupt 1, interrupt for the port switches. Okay, that's why and you can see transmission and receiver. There are different parallel flow port and we have serial data interface and serial clock interface for the IP channel and capture purpose. So this using everything is having multi-functionality. RD code. This is fixed functionality like digital input. When you see other functions functionality, either this one or this one. This is multi-function. Okay. So how the input output ports, how to access input output ports. Basically all these 5 ports, right? Port A, port B, port C, port D, port E. So all the pins are multiple. Okay. So all the pins are addressed directly by using the register. There are registers called pins, and so it's in the next slide. So it's having 8 input outputs. So basically port B, C, D, all these having 8 pins, right? As I told you here. So each port is identified with again special function. I told you right, this is a digital input output structure, right? So it's having special function registers to access them. Okay. So this is the special function output. So this is like any digital input output. Whether you want to access the input or output, how to access it. So these are the registers which are present in that. This is the register which indicates the direction of the port pin. If you set as 1 in the corresponding bit, the corresponding port pin will be input. If you set as output, the corresponding port pin will be output. Okay. So like this, 1 for input and 0 for output. So if you want to any write data, read the data or write the data, then port is the register which is used. Okay. If you want to change the data in the port, then you can use flag register. So for this one, you can go to you can verify the tick dot which is there. Then you go for input output port and you can see what is the register present in the port flag. How to access these registers. Okay. So now we'll see about what are the development. So every architecture supports as the architecture supports cross compilers. Okay, why is on there are two types of compilers, right? Native compiler and cross compiler. But we can't use native compiler here. Why? Because native compiler is only for the host is same architecture and the target is only same architecture. But we have to develop right application in the PC, our PC, and we have to execute in our target. So that is in the microcontroller. So we need to use cross compiler. So for the PIC architecture, there is a microelectronic like component and the some microchip tool. Okay. The microchip we have identified the development we have used for generating the application. So how to use the microchip tool and what is the advantage of microchip that we see in the another video. Okay. And we have a simulator for how to install all these things. Okay. Suppose for writing the application it supports some IDE tool for verifying the stuff and in the simulator. That means whatever the output